As we move on to chapter 16, number 37, here we're asked to, first of all, predict the sign of the change in entropy, and then to calculate it. Now, since we're not given these numbers right in the problem to calculate the change in entropy, you probably assumed that you were supposed to go back to the appendix, back in the back of your textbook, and look these up. So first of all, let's look at this and predict what the sign is going to be. Now, that's going to be really important in a lot of your test questions. A lot of understanding these equations is to be able to predict, and then when you get to the end, kind of check and say, does that make sense? Does this match my prediction? So here we're going to use the same technique we used in some of the previous problems of just looking at moles of reactants and moles of products. And also in this one, we've really got to keep in mind that what really drives entropy is the fact that gases are so much greater entropy than solids. And so if we have gases and solids mixed in a problem like this, it's really the change in the number of moles of gases that are going to help us decide if this has a negative or positive entropy. And because in this we're starting with 4 moles of a gas, and we're going to 2 moles of a gas, the change in entropy is going to be negative. So delta S, we're going to expect, is going to come out to be negative. So let's calculate it. Of course, to calculate it, you remember we're going to use this equation. It's on your equation sheet for the AP chemistry test that you'll be able to use. The sum of the standard entropy of a reaction is the sum of the standard enthalpy for the products minus the sum of the standard enthalpy of the reactants. Now, in your equation sheet, your AP equation sheet does not include, let's see, got to get a pen here, does not include this term that has the number of moles. But it's good to be sure you're keeping that in mind. So let's look those up and substitute in those values. So remember, it's the the products minus the reactants. So we have 3 moles of sulfur in the rhombic form. That's this 3 right here, 3 moles of sulfur, and 2 moles of water. So we're multiplying those by their entropies and adding them together. Then we're going to subtract 2 moles of H2S times their entropy. And we're also going to subtract 1 mole of SO2, because that's how many there are. Notice we're subtracting both of these. You could add them together and subtract the total, or you can subtract them, kind of one at a time as you're going through here, whichever works best for you. But you should get an answer of negative 186 joules per Kelvin. Now, did that match our prediction that we were going to get a negative delta S? Yes, I think it did. Of course, if you don't have your units on your answer is pretty useless. Don't forget to have your units there. B. Here we're looking at, well, first of all, let's predict the entropy of this reaction. Is it going to be positive or negative? Well, it appears that we're going from 2 moles to 3. So we're increasing the number of particles. So we're going to be increasing the disorder in the system, increasing the entropy. So let's calculate that. We're going to use the same formula we used before. And we have, we're doing products minus reactants. And so here's our 2 moles of SO2 times its entropy times 1 mole of oxygen in the gas form times its entropy. And then we're going to subtract 2 moles of SO2 and then times its entropy, and then we should be done. And we predicted we were going to get a positive entropy. Did you get a positive entropy? You should have gotten plus 187 joules per Kelvin. Moving on to 37C. Predict the sign of the change in standard change in entropy and then calculate it. Well, let's look here. How are we going to predict the sign here? Now you'll notice here we're going from 3 moles of a gas here to 3 moles of a gas here, and we've got this and some iron, and it is not going to be easy to predict the change in entropy of this reaction. So I think we're going to actually have to calculate this because it's just not going to be easy to predict it from what we're seeing here. So let's use the same equation we've been using. We're going to start with the finding the sum of the entropies of all the products. So we have 2 moles of iron times its entropy that we looked up in the back of the book, and we have 3 moles of water in the gas form times the entropy that we look up in the back of the book. And then we're going to subtract the entropy of the reactants. So here's 1 mole of this reactant, the red iron oxide, otherwise known as iron 3 oxide, and its entropy minus, we're also subtracting the entropy of 3 moles of, oops, why did I write H2O? I think that's just H2 there, and double checking my work back here to make sure I have the right number, 141. This is 37C. Yes, it should be. I've got the number right. I just wrote an O there for no good reason. Okay, let's add these and then subtract these, and you should have come up with a positive change in entropy for this reaction of plus 138. Okay, let's see. Let's go on to number 38. Same kind of problem. Let's predict the sign. Now this we should be able to predict the sign because we're going from 1.5 moles, 1.5 moles to 1 mole. So we're actually compacting this and we're making it less spread out. So we should have here a, I'm going to predict a, what did you predict? A negative change in entropy, I hope. So remember, we're going to use this same equation that we've been using. So here's our product, 1 mole of H2O. And its entropy, and then we're going to subtract the reactants, 1 mole of hydrogen and 1/2 mole of oxygen. Don't forget to divide that by 2. Now we're going to add those together, and did we predict a negative change in entropy? And there it is, negative 164 joules per Kelvin. Moving on to 38B. Let's see, we're going here from 5 moles, and those are all in the gas form, to 6 moles. So we're kind of spreading this stuff out a bit, aren't we? We're burning methanol in the presence of oxygen. We're making CO2 and water, and both in vapor form. It's spreading out. I'm going to say this should be a positive change in enthalpy. So let's add together the enthalpies of all the products. 2 moles of the CO2 times its enthalpy, 4 moles of water times its enthalpy, and then let's subtract the enthalpies of the reactants, and we should calculate 89 joules per Kelvin. Sure enough, we got a positive enthalpy. Let's look at 38C. 38C, I would predict a positive change in enthalpy here. Let's see. No. Because we have a gas here, remember, gases really dominate the predictions of change in entropy. And so if we have a gas and we go into a water solution with that gas, we're probably going to be putting the particles much closer together. And so it's going to become probably more orderly. So let's predict a change in entropy of more orderly, less disorderly, negative change in entropy. So let's calculate those. And here we'll notice because of some energy changes going on in the formation of these ions, we actually have an ion that has a 0 for the entropy, and an ion with 57 for the entropy. And then let's subtract the entropy of the gas, the HCl gas, and so we're subtracting 187, and so we're going to come up here with a negative 130 joules per Kelvin.